I'm going to talk about fast radio bursts and their links to magnetars. Fast radio bursts are obviously one type of radio transients. There are many different examples of radio transients, and in this plot you can see them, at least some of them. On the horizontal axis we have more or less the width of the transient, so the duration of the transient, and on the vertical axis we have luminosity. So there are different types. We can see radio pulsars here, gamma ray bursts, active galactic nuclei, and duration and luminosity of these transients are very different. However, it is very difficult to find a very short transient if it was not known before. So it is easy in the radio waveband to find a transient if this is a transient activity of an already known source. That's one option. Or it is easy to discover a transient if it repeats very often. But it's very difficult to find very short transients which appear in an unexpected piece of the sky. This is so because there are lots of noises in radio, and everybody who tried to listen to the radio at short wavelengths definitely knows that there are lots of noise in this. So only in this century it was possible to discover new classes of very short transients. And the first interesting result in this field was the discovery of so-called rotating radio transients. You can see them here in red, just in the middle of this plot. Rotating radio transients actually are neutron stars. They are not much different from radio pulsars, but somehow they are different. And up to now we do not know for sure what's the exact difference between emission mechanisms of normal radio pulsars and rotating radio transients. But the second discovery made a few years later was really miraculous. This was discovery of what we call now fast radio bursts. And in this plot you see them in the top left corner. You see how significantly they are separated from all the rest sources in this figure. So they are very short. The typical durations are indeed in the range of milliseconds, and they are extremely powerful. So we didn't see anything like this before, and when these sources were discovered in 2007, they became a big mystery. But let me give you a brief introduction in the history and astrophysics of fast radio bursts. So the brief history is like this. The first paper was published in 2007. Actually, the burst was observed 6 years before. But it took some time to find such an interesting event in the archival data. So it is necessary to use quite a complicated algorithms to look for such short transient events. And so in 2007, in the paper by Dan Lorimer and his collaborators, this event was announced. In the left bottom corner, you see a plot from this paper. What you see here? We all know that the velocity of light is 300,000 kilometers per second. This is in vacuum. Actually, the interstellar and intergalactic medium is plasma. And radio signals, for example, propagating through this medium propagate with different velocity depending on their frequency or depending on their wavelength, whatever you like. And signals emitted at short wavelengths, at high frequency, propagate a little bit faster. And we can measure it. We can measure a short spike different wavelengths, and we can see this dispersion, this kind of delay. And this is shown here. On the vertical axis we have frequency. The mid frequency is about 1.4 gigahertz, 1.4 gigahertz. This is this 21 centimeter wavelength, quite often used, for example, for radio pulsar observations. And on the horizontal axis we see delay, and we see that the signal was a very short spike with millisecond duration. It is shown here, and the signal was significantly dispersed. This means that the signal propagated through a huge amount of medium. Of course, it can happen if it just propagates through a dense cloud, but it's more natural to assume that it just propagated for a long time, for a long distance. And so it collected this medium on the way of the signal. And immediately it was clear that the signal might be extragalactic. So what people observed, a very short, a very intense radio burst, which didn't appear any time after this observation, and it was extragalactic. It didn't look like something known, and even worse, or even more interesting, it looks very peculiar. It was not like any other event. However, that was a single signal, and in 2007 the astronomical community didn't react with many papers trying to explain it. We had to wait for a few years more. The second event of this type was announced only 5 years later, but even in 2012 nobody tried to start a very big discussion. The big discussion started in 2013 when in the paper by Thornton and collaborators, the authors announced 4 new events. They are shown in the plots on the right. So again, they were 4 very short, very intense radio bursts. There were no repeatings of them from the same direction, and they looked extragalactic because they all had this significant delay. Significant dispersion measure was determined for these sources. So from this moment, people started to write many papers with different theories, and in the second part of my talk I'll mainly speak about these theories, and I'll discuss where we're standing now, what are achievements up to now, and what are unanswered questions we're thinking about at the moment. Then I mark another date, 2016, when the first repeating source was reported. This was quite important, and a few slides later I'll explain why. Okay, so let me say a few words about the first event. It was discovered with 64-meter antenna with a Parkes radio telescope in Australia. You can see it on the right. People were just surveying the sky, and they observed a rather unparticular piece of sky close to the small Magellanic Cloud. You see the picture on the left, and these 13 small circles, they are 13 radio beams. In these circles the telescope was sensitive, and the telescope observed a very intense, very short flare. You saw it on the figure in one of these beams. The intensity was really large. The fluence was 30-40 Jansky. This is a lot because radio telescopes are sensitive to sources with millijansky, and here this is a very bright flash in radio. But as I told you already, it seemed that the source is extragalactic and is situated really far away. And below we see a formula. So what we have flux normalized to 1 Jansky, frequency normalized to 1.4 gigahertz. At the end we have distance normalized to 1 gigaparsec, so slightly more than 3 billion light years. And this parameter omega describes how collimated is the burst. Sometimes sources emit isotropically, the same emission in all directions. Sometimes they are strongly beamed. We don't know if radio bursts are beamed or not in this case, and so it normalized for 1 steradian. The whole sky, the whole sphere is 4 pi steradian. So it is in this equation the normalization corresponds to mildly beamed event. And we see that already with this normalization the luminosity is huge, 10 to 41 ergs per second. I remind you, let me recall that the luminosity of the sun, the solar luminosity, is 4 times 10 to 33 ergs per second. Here we have much more, and in radio. For example, our sun in radio is a very dim emitter. Here huge energy is emitted in radio, and let us recall another important thing. It is very seldom that any source emits mostly in radio. So if we see some radio emission from a source, we suspect that there might be even more significant emission with larger luminosity in other parts of the electromagnetic spectrum. So the source looked very peculiar, and it was necessary to explain it. The first event, as I told you, was discovered in archives. The second, the third event, they are all discovered in the archives. They are short flashes, and of course you have a question: was it possible to observe something else from this direction in other ranges of the electromagnetic spectrum? The answer is unknown. So nobody looked particularly in these directions before when this archival data was taken. But in May 2014, for the very first time, a burst was identified online. So it was identified very quickly, very rapidly, and it was possible to trigger a follow-up observations. And this was very important. So people immediately started to look in the same direction with optical telescopes, with X-ray telescopes. Definitely gamma ray detectors could trigger something from this direction. They typically perform more or less all sky surveys. And the result was absolutely negative. They found nothing. And this was quite interesting, because typically what we expect, if we have a strong burst, then we suspect that there was, for example, the first idea we have, a strong explosion. What explosions we know? Supernovae. Perfect. If there was a supernova flash, we might see it in optics. But we see nothing. So supernovae are excluded as explanations of fast radio bursts. What else? We can have a gamma ray burst. Again, do we see something in X-rays or in gamma rays? Nothing. So we exclude these sources as an explanation of FRBs. So actually this was quite an interesting result. Until now, people actively tries to observe simultaneously fast radio bursts with other types of telescopes, and till now there are no counterparts in any other wavelength. Okay, so we do not see sources with other types of telescopes. That's a problem. And that's a problem because we cannot actually well localize the source. At least we could not till some moment. So we'll come to it later. What could the Parkes telescope do? We see these 13 beams in the sky, and the telescope could say just that the burst was inside one of these small yellow circles you see in the screen. This is not enough actually to localize the source of this burst well enough, because this yellow circle is quite large. For example, this large circle you see on the screen is more or less of the size of the moon on the sky. So in the area of the sky equal to this yellow circle, there are many interesting galaxies, or something is happening. You cannot say where exactly, at what distance the source of your radio flare is situated. So localization was quite a problem, and it was necessary to discover the first repeating burst. The discovery of the repeating burst was important in many respects. The first one is obvious. If it is repeating, then there was no catastrophe. So you exclude any catastrophic scenario which completely destroys the source of these bursts, because they repeat. They repeat quite often. There are many repetitions, many new bursts from the same source. So we absolutely exclude these all catastrophic scenarios. But another good news with repeating source was that now it was possible to determine position exactly. So the first source, typically they are named like this. Let me explain. FRB stands for fast radio bursts. And then the date of the first discovery. So 2012, November the 2nd. The first event from this source was discovered on this date. Now there are many bursts per day, so people add letters after that, A, B, and so on. But at that time, in 2012, observations of these bursts were not so frequent. You say repetitions, and then it is possible to pinpoint the source exactly. And this source was the first example, the first source of fast radio bursts, for which it became possible to determine its position with huge precision. It happened so because it was observed with the VLA radio telescope system. Actually, even more. It was simultaneously observed by many radio telescopes, and we see it in this plot. Along the horizontal axis, just the time is running with the different dates of observations. And the source was observed with 4 antennas, or with 4 sometimes clusters of antennas in the case of VLA. It's not a single antenna. Those with circles correspond to detections of burst. So here, for example, they looked at the source, but VLA detected nothing. And if we have a circle, it was detected with VLA. And if these observations are connected with the solid line, then it means that simultaneously the source was detected by several instruments. It also helps to determine the position of the source with huge precision. But even VLA is enough. So for the very first time, we exactly could measure in which galaxy the burst appeared, and even more in which part of this galaxy it appeared. And the result was quite interesting. So the first discovered host galaxy of the fast radio burst was a dwarf galaxy with large star formation rate. So this immediately tells us that sources might be related to massive stars or to their products. For example, young neutron stars or maybe young black holes. But the main outcome was that it fitted well for models with young neutron stars. As we'll discuss later, at this time, at the end of 2016, beginning of 2017, you see from these numbers, maybe I have to remind, that these numbers are numbers of papers in the archive, in this, which these papers you can find at the website archive.org. And 1701 means that these papers were published in the archive in January 2017. Coming back, at that time already young neutron stars were the best hypothesis to explain fast radio burst. However, other hypotheses were still under discussion. But discovery of this type of host galaxy was a very good news for those theorists who suggested or defended, developed models with involving young neutron stars. As we know the galaxy, we can exactly determine the distance, and the distance was indeed about 1 gigaparsec. So this means that everything before was correct. We correctly identified sources as extragalactic. There are no tricks. They are indeed far away, in a faraway galaxy. And this was a very important achievement, and it helped a lot to understand better sources of fast radio bursts. But definitely that was not the end of the story, and even not the middle of the story. Yeah, here I have to also to underline that the source of fast radio bursts, this one, the first repeater, is also visible between bursts, and up to very recent time, this was a unique characteristic. So there was a very compact radio source, persistent radio source, coincident with the source of FRBs. And only very recently, this October, so a few weeks ago, it was announced that there is another source which looks like more or less a twin of the first repeater. It is also a repeater, also in a dwarf galaxy with high star formation rate, more or less at the same distance, with very large rate of bursts. So it demonstrated 75 bursts in 19 hours of observations. This is really a lot. And it is also coincident with persistent radio source. So now we know that the first repeater is not really a unique source. It's also a good news, because in astronomy it often happens that we identify some group of sources, and then there is one very well started source inside this group, but the source looks peculiar, and later on it comes out that the source is not very typical for this group. It's not a brother, it's like a cousin. And the fact that now the first repeater is not a unique source is, in my opinion, quite important. Okay, since that time many sources were localized, and up to now there are about 20 localizations made with different instruments, with different techniques, and the achievements are really impressive, because now, for example, with ASCAP, again it's an Australian instrument. This is Australian Pathfinder for SK, for the Square Kilometer Array. So this system of radio telescopes, again, this is a system more or less like VLA, but different, similar to VLA. So this instrument can identify positions of non-repeating sources with high precision. And few other instruments also can do it, so it's quite important. But I'll mention just two localizations which seem to be very important. So this is the first example. Actually, it was the fifth localization, as you see in the title of the slide. The source was a repeater. It is a repeater. It continues to emit fast radio bursts. We see them. It is situated in a spiral galaxy, as you see, with large star formation, and at that time it was the closest source of FRBs. This is quite important because, of course, if a source is closer to you, you can see dimmer bursts, you can put better limits at other wavelengths, or you can hope to find counterpart at other wavelengths. So for some time I'd say that this source was maybe the most observed source of fast radio bursts. And another interesting discovery was made in relation to particularly this source. And here it is. We observe bursts, so it's like click. And if you collect lots of them, you can start thinking, are they really repeating or not? So do they come randomly, or there is some period between them? And definitely for the first repeater people tried to look for such periods for the second and so on, but only with this source, and partly because it emits lots of bursts, and people spend lots of time observing particularly this source. It became for the first time possible to find a period. The period is about 16 days. You see the exact number in the slide. And the period is, it's not like the period that, for example, every day at 9:15 in the morning I enter my institute or enter the door of my lab. No, it's not like this. It's more like that. On Monday, I appear in my lab, and I do not appear in my lab on Tuesday or Wednesday. Now, with all these lockdowns and pandemic, this is all right to appear in the institute once or twice per week, for example, when I have lectures. So you can find me at the institute on Monday, and you cannot find me any other day. But on Monday I can come in the morning, or I can come after lunch. So this source works like this. So there are some periods of time in which you can detect bursts, and then nothing. And after 16 days, this period with high probability of bursts is repeated. And again, you can find the burst, but definitely not every Monday I can come. For example, well, I had COVID myself, for example, and I was not lecturing for several weeks because of this. So not every period of activity this source is actually active, but the activity happens only during these restricted periods. And this is quite interesting. What can be the reason of this periodicity? Because if you correctly identify the origin of this periodicity, you can hope that this can be a major step towards the final identification of the nature of these sources. Definitely with this 16 days period, the first option is that this is an orbital period in a binary. And indeed, several papers appeared by different authors. I do not pretend to make a comprehensive review of the subject, so I do not refer, for example, to all models with binary systems. But the idea is that the source is working continuously, but only in some positions you, as an observer on Earth, can have a possibility to detect the burst of the source. For example, during all other period of time, all other phases of the orbital period, the signal is blocked by plasma inside the system, and there is a window and which is transparent for this emission, and every 16 days you look into this window and you can detect a burst. That's one idea, and many people like it. Another idea is quite different. Neutron stars can precess, and if these FRPs are significantly beamed, is the emission is very much collimated, then precession, of course, changes everything. So with this precession period, the situation changes. Either the beam is pointing towards you or not. And of course, you detect bursts only when the beam is pointing towards you. Thus, you have the 16 days periodicity. This is also possible. Up to now, we don't know the answer. And I think this periodicity is quite an important thing. And I'll say a few words about it near the end of my talk. There is only another example of periodicity in fast radio bursts. In this case, the period is roughly an order of magnitude longer, and no miracle, this is the first repeater. This is the source FRB 121102, from which the largest number of bursts have been detected during all periods of observations. And again, in this case, both ideas, binary system or precession, can work. Okay, one of the latest identification is really peculiar. So it looks like a miracle, but I would say strange miracle, not very pleasant miracle, at least for me. So a fast radio burst was detected from a very nearby galaxy, from M81. You see this galaxy on the photo, and I believe that many of you saw this galaxy before, maybe even with your own telescopes, because it's quite easy to see it as a spot in the sky, even with a small instrument. So the first good news is that the source is very nearby. Now it's closer than 4 megaparsec. Perfect. But it brings problems because it's not, for example, somewhere in the spiral arm where star formation is active. There are many massive stars, many supernovae, and so many young neutron stars. No, the source is in a globular cluster. And this is really strange. This is really peculiar, and we'll discuss it later when we come to models. Please remember, it's a very interesting puzzle, how you can link together facts that some sources are in regions of very active star formation, and this source is in the region where you do not expect any star formation for billions of years. This is quite interesting. And there are interesting ideas how to overcome this difficulty. Okay, so my first introductory part is finished, like expected, half an hour for the introduction, and roughly another half an hour or slightly less to speak about theories. Okay, so let me talk about theories. We have to start from bottom left corner and move towards top right of this plot. What we have here, in 2007 or if like 2013, when FRBs have been discovered, there are many interesting ideas. Some of them were rather exotic: cosmic strings, primordial black holes, gamma ray bursts, supernova of exotic types and exotic radio emission, some peculiar processes with white dwarfs, even white holes were suggested. That was quite an interesting paper. And the second branch of thinking, the second route, was related to neutron stars. And quite early, neutron stars began to win over all other hypotheses because the rate of burst is high. So let me, for the first time, name it. At the sensitivity of present-day telescopes, we can observe, or say we could observe, several thousand bursts per day on the whole sky. So if we have ability to observe, for example, with Parkes, all the sky continuously, 24 hours per day, every patch of the sky, then we will detect several thousand bursts in a day. That's really a lot. And this large rate excludes many exotic models. On the other hand, the rate is not that high. It's much less than the rate of supernovae in the universe, for example. So you can exclude some models because they are not so rare as fast radio bursts. But neutron stars fits perfectly well. So that was the first dichotomy, the first division, and we follow this route. Neutron stars. What with neutron stars? On one hand, so on the left hand here, you can think about exotics related to neutron stars. With fast radio bursts, I think that's a very useful note. With fast radio bursts, initially you could discuss many interesting exotic scenarios. And this is quite interesting and useful for development of astrophysics, of physics, because sometimes you have some interesting ideas in your head, but really to discuss it broadly, you need some motivation. And discovery of a new phenomenon gives you this possibility. So you have this motivation to discuss your very exotic model, and many exotic models were discussed. So even if they are wrong in application to fast radio bursts, I insist that it is useful to make careful, of course, discussions without arithmetic mistakes, not violating laws of conservation and so on. But you might discuss, if you are a theorist, you might discuss interesting ideas if you have a chance. So there were many interesting exotic ideas related to neutron stars, starting from coalescence of neutron stars which is not so exotic, then deconfinement, supermassive neutron stars, axion clouds entering magnetospheres of neutron stars, asteroids falling on neutron stars. So many interesting ideas, but all these were more or less closed by repeaters, because definitely you cannot make coalescence several times with the same source. But even with axion clouds or asteroids or something else, it's very difficult to make, for example, 75 bursts in several hours. So we follow a more traditional route. Some can say that it becomes more dull, exotics is not working, but it's always a place for exotic, I would say. It means that even if you follow a dull route, more or less normal neutron stars, you can discuss very interesting emission mechanisms. So still there are many interesting things to do with fast radio bursts. So we have repeaters, and we come to another crossroad. Now there are two main ideas, and later on I'll speak about it a little bit longer. So either we are dealing with something similar to radio pulsars. Maybe you remember in the very first picture I showed, there were giant pulses of radio pulsars. There are pulses of normal galactic pulsars which are very intense. If you make them even more intense, even more powerful, they can start to look similar to fast radio bursts. So that was the first idea. And in this case, what is really important from the physical point of view, the rotational energy of a neutron star is emitted, because pulsars, normal radio pulsars, are emitting rotational energy. Another possibility is related to magnetars. Magnetars are neutron stars which are visible because they are emitting the energy of the magnetic field. Typically they have huge magnetic fields, and dissipating the energy of the field, you can either hit the crust of the neutron star or emit bursts. We are quite familiar with this because solar flares are also related to the magnetic energy dissipation. And I would say the last major discovery in the field of fast radio bursts, which happened just last spring last year, was the discovery of a fast radio burst from a galactic magnetar. That's its name, actually part of the name, and we'll discuss it later. So now we think that we have to follow this route. We know that magnetars are sources of fast radio bursts. And anyway, it's not the end of the story. We still have two questions. The first question is not shown here, but we'll discuss it in several slides. The first question is related to the emission mechanism, where the emission is produced. And the second question is related how these magnetars are produced. Because there is a normal way to produce magnetars, core collapse supernova. Neutron stars are produced by massive stars at the end of their revolution. Their cores collapse and form a compact object. So collapse stops, they do not form black holes in this case. And some of these neutron stars, now we think that about 10%, can have very high magnetic fields, so we can observe them as magnetars. So that's a normal way to produce magnetars. And in this case, we have to deal with very young neutron stars, because all known magnetars are very young. Why? You can ask. That's a good question, a reasonable question. Because they dissipate the energy of their magnetic field relatively quickly. How quickly? In 10,000 years, maybe in several tens thousand years. Of course, it's much shorter than the lifetime of a galaxy, for example, which is 10 billion years. So these normal magnetars might be related to regions of star formation. However, we see, and the best example is this magnetar in a globular cluster, we see magnetars absolutely unrelated to regions of star formation. And then we need exotic mechanisms to form magnetars. And this is interesting. So as I promised, we come to new exotics. There are 2.5 possibilities to form a magnetar in an exotic way. So the first way, coalescence of two neutron stars. Two neutron stars can form a binary system, and they can live a long and maybe happy life. And maybe after a billion of years after they were formed, they coalesce and form a neutron star, which might look young, and it can have a large magnetic field. Because the process of coalescence is a very complicated and powerful process, and you can enhance magnetic field during this process. The other way is coalescence not of two neutron stars, but for example of two white dwarfs, or a white dwarf and a neutron star. Also it can produce a magnetar. Or you can have so-called accretion-induced collapse of a white dwarf. If you take a white dwarf and start to add matter step by step, then at some moment you can reach the Chandrasekhar limit and the white dwarf collapses. And this collapse can result in formation of a neutron star, and this neutron star can be a magnetar. So there are these exotic ways to form magnetars, and the answer to this question might be related to our observation of host galaxies of fast radio bursts, so we'll discuss it later. That's the present day situation. Now we just discuss all what is shown in this slide in more details. Very briefly, I pass through some interesting but rejected models, just to name them. Coalescence of neutron stars, suggested by Tatani, immediately after the paper by Thornton was published. Asteroids falling on neutron stars. By the way, the same mechanism was discussed like 30 years ago, maybe, for gamma ray bursts. I remember papers I've read when I was a student. Another mechanism, collapse of a so-called supramassive neutron star. After a coalescence, you can form a neutron star which is stable only because it is rapidly rotating. But as it slows down, and it happens quite quickly in hours or days, depends on the situation, as it slows down, it can collapse. It can collapse to a black hole, or it can collapse to another neutron star. Typically, we discuss collapse to a black hole in the case of supermassive neutron stars. And this, as was suggested by Falke and Rizzola, can result in a fast radio burst. Then this model of axion clouds, it was suggested independently by two papers, by Igor Tkachov and by Vadzaki. And deconfinement. Deconfinement is a very interesting process. You know that protons and neutrons are made of quarks. And in a normal world around us, there are no free quarks. They are all confined in protons and neutrons. But in neutron stars, density is very high. And you can have a transition from normal matter made of protons and neutrons to quark matter. And this process is called deconfinement. It can happen spontaneously. There are models of this type. And it was suggested by David Alvarez Castillo and his collaborators that this can result in a fast radio burst. However, many models were rejected, partly because repeaters were discovered, and repeaters definitely exclude, as we already discussed, all catastrophic scenarios. And as repeaters very often are identified with galaxies, you can exclude many other scenarios. For example, cosmic strings have nothing to do with galaxies, and you simply reject this idea. Okay. Magnetars very quickly were proposed as sources of fast radio burst. Actually, we wrote a paper with Konstantin Pasnov just a few months, or even I'd say weeks, after the paper by Dan Kloremer. The reasoning was quite simple. We estimated the rate of very powerful flares of magnetars in the universe, and the rate was consistent with the rate of fast radio bursts. The time scale of these giant flares or hyperflares of magnetars is also consistent, because the rising front of the flare has typical time scale of several milliseconds. Absence of counterparts, it fits, because if a hyperflare of a magnetar happens somewhere at 1 gigaparsec from us, we don't see the flare itself. We can see it only in radio, because in radio we can reach much better sensitivity. We can detect much lower fluxes on Earth, partly because just we use huge telescopes for it. And energetics is fine. The total energy of a hyperflare can reach 10 to 46 ergs, and you can use a tiny fraction, 10 to minus 5 of this total energy, to produce a fast radio burst. In our paper in 2007, there was no detailed physical mechanism proposed. We just proposed and defended the idea that giant flares of magnetars can be sources of FRBs, and demonstrated that it fits. But already at that time we could refer to the model by Maxim Lutikov, published a few years before. And later on, magnetars attracted much interest in relation to fast radio bursts. And as I said, now it's the idea number one. And there are many models proposed, developed with quite complicated physics. And this story definitely is not finished. So there are lots of things to be done. The second idea related to neutron stars was related to these giant pulses. As I told you, some pulsars, and in particular the Crab pulsar, the most known radio pulsar, sometimes can emit very powerful bursts. Of course, the larger the energetics of the burst, less frequent they appear. So you can see it on the plot. We have the rate on the vertical axis and energy, actually fluence on Earth, on the horizontal. And if we, just by hand, we don't observe it from galactic radio pulsars, but if we continue this line, we can suggest that with this extrapolation, we can have relatively rare but very powerful radio flares from radio pulsars. However, there are some problems with this mechanism, and I'll discuss some of them on the next slide. But this idea was discussed in details. Actually, we mentioned it already in our paper in 2007, but really we just mentioned, we didn't develop it. I recall that it was even a footnote in the paper, that if you rescale these bursts, they also can fit. But people developed detailed models, and here are the problems. If we are dealing with super giant pulses, then we are emitting rotational energy. The source of rotational energy, the amount of rotational energy, is huge. It's larger than the energy in the magnetic field. But it's much more difficult to take this energy from a neutron star. And you really need very large efficiency. But if you have large efficiency, if you put nearly all energy in radio emission, you have another problem. You are spinning a neutron star too rapidly. And this means that the period, the properties of this neutron star might change nearly during your observations. And now, for example, the first repeater is observed continuously for nearly 10 years. And we do not see any significant changes in the source. So it works against the model with a large spin down of a neutron star with rapid braking of a neutron star rotation as the source of energy of fast radio bursts. But of course, the main discovery which gave support to the magnetar hypothesis was discovery of a fast radio burst from a galactic magnetar. For quite a long time, people criticized the magnetar model, and they were saying, but where are flares from galactic magnetars? We know about 30 galactic magnetars, and there might be a few tens more, but none of them showed fast radio bursts till April 2020. On April 28 last year, the CHIME radio telescope and another interesting radio instrument called STARE-2 detected a fast radio burst, and they could identify the position approximately, not with huge precision, but exactly at this moment, and from the same part of the sky, 4 space instruments detected a flare from a well-known soft gamma repeater, the soft gamma repeater 1935. And these 4 satellites were Russian detector KONOS on board of American satellite WIND, the European satellite Integral, the Chinese satellite, and the Italian satellite Agile. So all their results are consistent with one another, and as we see on the left, that's the results detected by KONOS experiment. We see that the high energy burst shown in black here in 2 energy ranges is exactly coincident with the radio flare which is shown with blue. It was a double fast radio burst, so there are 2 blue strips here. They are perfectly coincident in time, they are coincident in the sky with the precision we have, and it was a clear detection of an analog of fast radio bursts from a galactic magnetar, coincident, which is important, with a flare of a magnetar. Even more, it was shown by different groups that this particular high energy flare was peculiar. You see it on the plot on the right. It's even not important what is shown in the axis. Simply black shows normal bursts of the same magnetar. Numerous tens of bursts have been detected from the source, and in blue this peculiar flare coincident with an FRP is shown. So it is significantly shifted. Now we can say what is in this axis. So flux is in the horizontal axis, and the typical energy, typical spectral energy on the vertical axis, and this flare is much harder than all the rest. So now we think that sometimes magnetars produce peculiar flares which also produce radio emission, which we observe as FRBs. If this is a dim high energy flare, we have a dim radio burst. If it is a giant or hyperflare, then we observe a normal fast radio burst, which can be detectable from really extragalactic distances. So now there are many models of emission, really detailed, very complicated models, developed for magnetars, how they produced fast radio bursts. I'm not going into details. If you are interested, I suggest to look in papers by Andrei Beloborodov, Brian Metzger, and others. I just want to underline that there are now 2 different types of models. In one type of model, defended, for example, by Beloborodov and Metzger, the emission is produced in a relativistic shock relatively far from a neutron star. So there is a burst, a high energy burst in the magnetosphere of a neutron star. The signal propagates, then it reaches the outer shock, and radio emission is emitted there. The second class of models predict that radio emission is produced exactly in the magnetosphere of a neutron star, And now, from theoretical point of view, this is maybe the major puzzle in physics of fast radio bursts. Either emission is produced in the magnetosphere, or it is produced in a relativistic shock far from the surface of a neutron star. So this is the main direction in which theorists are working now. All this situation is nicely reviewed in a relatively short review by Bing Zhang, published last year in December in Nature. So as it is published in Nature, it might be a very short paper. And the good news is that it is also available in the archive. Here is the number. And if you are interested in the subject, I strongly suggest to look at first, if the subject is new for you, to look at first in this review. What are arguments in favor of one or another scenario, relativistic shocks or magnetospheres? There is a very interesting piece of information from the FAST radio telescope, the largest radio telescope on Earth. They measured polarization of radio emission of a repeating source. And they showed that in the case of one source, the polarization properties are rapidly changing from burst to burst. And this feature points towards the magnetospheric scenario, because conditions can be different in different parts of the magnetosphere. The star is rotating, you observe different parts of the magnetosphere, and no miracle that different bursts have different properties. If everything is produced in the outer relativistic shock, it is quite difficult to make different bursts looking different. So somehow I would say that at the moment magnetospheric models maybe are slightly more promising, but we are really far from the final answer now, and lots have to be done by theorists, of course, and of course by observers, because we need more observational keys to solve the puzzle of the emission mechanism of fast radio bursts. Okay, periodicity, what does it tell us? That's another interesting thing. Sometimes people put forward hypotheses that the most intensive repeaters are peculiar magnetars formed in some exotic way, for example, due to coalescence of objects. And if this is the case, then of course periodicity cannot be related to binarity. And then it's quite important to identify the origin of this periodicity. If it is precession, maybe this is an argument in favor of exotic mechanisms of magnetar formation, at least in the case of two periodic sources. If it is proved that the origin of the periodicity is related to binarity, then definitely we have to exclude exotic mechanisms of formation. Formally, you can work with triple systems, but in my opinion, it's like to use epicycles, and it's not so natural. The rate of fast radio bursts at the moment doesn't tell us much. Just the good news is that even with new measurements, with the source in M81, with the galactic magnetar, more or less everything is consistent with the magnetar scenario. So this is not maybe the most important frontier of the present day studies. But what is really important now is to study host galaxies, because here the situation is very controversial. There are not so many identifications now. Some of them, as you saw already, are very peculiar. And when people try to do some statistics with these roughly 20 identifications, they come to contradictory results. There are papers, several papers, as you see, that everything can be explained with normal magnetars. Normal means that they are produced in core collapse supernova. Some papers insist on quite opposite conclusion, that we really need exotic magnetars, or even there are claims that everything is more consistent with exotic magnetar formation. So this situation is not clear at all, and on other hand, I can expect that as the number of identifications will grow significantly in the following years, in the following 2-3 years, because new instruments appear now. The Meerkat instrument in the South Africa is intensively studying fast radio bursts. As the number of identification grows, we can expect on one hand just increase of statistics, on another hand we can expect some interesting discoveries which can shed light on the question of origin of magnetars. So what's in the end? We have two major questions now. We were more or less sure, still there are dissidents, but we are more or less sure that magnetars are responsible at least for the major part of fast radio bursts. What we do not know, either the radio bursts are produced in the magnetosphere or in the outer relativistic shocks. Are we dealing with normal standard magnetars produced in this normal evolutionary channel, or we are dealing with some exotic sources made, for example, with coalescence? And definitely it's not necessary that all sources might be explained by the single evolutionary channel and single emission mechanism. They can be different as plugs we use in different countries, and when you travel up to now, sometimes it's good to have a different plug with you, otherwise you cannot plug your laptop at the hotel. But maybe, and I hope, they can be only one. At least this might be true for the site of emission and mechanism of emission, and for the origin maybe we are dealing with multiple population. So, so I'll stop here. Thank you.